Hello, people. Sorry about that delay. Some minor technical problems there. Right, here I am with Philip, and we're going to talk about ray tracing the image of the Isle of Man. And I'm going to do a quick sort of introduction to the background to this and a bit on refraction. And then Philip's going to tell us how he modelled the Isle of Man using his ray tracing software, and that will be absolutely fascinating. Right, so I'm going to quickly do a background introduction, and let's how we got here and why we're talking about the Isle of Man. And I'm going to need to know, first of all, I'm going to right, here we go. Right. Okay, so this all started, people probably know most of this, but I want to give an introduction for people who aren't familiar with it. This all started with a flat earther taking a picture of the Isle of Man, which you can see in the top of the image here. That's the Isle of Man from a place called St. Bees, and this flat earther, St. Bees in the United Kingdom. And they took a picture of the Isle of Man randomly, and a video, and they went to these cliffs in St. Bees in Cumbria, and they went up the area around here, took an image, and took a video of the Isle of Man from there, which is, as I say, was from the image at the top here, and they managed to get in their image, in their video, images such as these of the Isle of Man. This is using a P900. And they then used this as proof of the flat Earth. I'm using some images here thanks to Miles Davis and Al Kay and Hal Sort and Jen Panda and Paul Voigt and Dr. Jonas and a few others and George Natayuk. And oh god, these are some things I haven't unfortunately been able to prepare as much as I wanted to, so it's a bit off the cuff here. And he took a number of images here of the Isle of Man in the videos that he created, showing bits that he felt that he shouldn't be able to see, and he made claims like this one here that the images in these videos he managed to gain, which he felt shouldn't be there. He thought there were bits of Ireland, bits of Scotland, he's far too high. You can see this is the image of taken by a professional cameraman, professional photographer of the image, and these are two sample images that he felt were, as you can see there, he believed this was the end of the Isle of Man, and beyond here he felt this was either Scotland or Ireland, depending on the day of the week. And to the left, he also felt he could see Ireland. So this led to a lot of controversy, and he, from this vantage point up here on the cliff, he took two videos. These shots are from the first one, and he then constructed this. He took this video and he constructed this composite, which we can see here. I'll zoom into that. So this is what he actually took, and he made some number of erroneous identifications, including things like thinking this was the Douglas, the capital, and there's a whole series of claims here. And this is the Isle of Man, showing some of the interesting points. He, coming from St. Bees here, these are the lines of sight to the various points of interest, and he misidentified lots and lots of things. But that's this is a website that I'm going to be creating relating to all this. But we're just trying to deal with some of the claims they made, and Philip here is part of dispelling some of these images. And oh yes, one of the important points to understand is what this the scale of what's going on here. Yeah. So for instance, here we have a scale model of the Earth, and you can see here the distance between St. Bees and Douglas, Douglas being the capital of the Isle of Man down here, and St. Bees being here. That distance there is 68 kilometers to Douglas, and those lines form part of a great circle. And if you take a great circle, these are some of the claims, but we're not really going to go into that detail. We're just going to focus on Philip's stuff. but we need to set some background here. This is so we can see the scale of the distance between them, and that what sort of fraction that forms of the Earth's circumference, and what they get confused about what's up and down. But I'll say now this is actually a scale diagram of the situation between St. Bees and Douglas, and so you can see here that the curvature of the Earth. This is a scale model of the curvature of the Earth, and here on the right up here we have a picture of the of the cliffs. And if you zoom into this, you actually have I've actually got a picture here of actually to scale for the Earth here, and this is a Douglas. I can't remember if I didn't get around to putting anything in there. So that's what the actual Earth looks like. And this, so whenever we're talking about the bending of light, which is what the main focus of this discussion here is, and modelling it, you have to remember that's what. If we zoom into a little bit, so there's a straight line in here, so you can actually see. Oh, that actually has not bugger. There should have been a straight. Oh, great. I'm going to have to go to my other. Hold on a second. I'll have to go to my other diagram. I have managed not to include the. Brilliant. That's there. So I'm sorry. This is all not prepared. Ding, 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 ding. God. Sorry about this. Right. So in here, there we are. So right there, this is the same diagram, slightly modified, but with the extra bit that I needed. There you can see the same thing. That's what the curvature of the Earth looks like. And you might think that looks like a straight line, but in fact, there you can see there's a straight line joining the 2 points, and there is the curvature of the Earth. And that matches, I can't remember what the height of that bulge is there, but yeah, I should have. Oh, the other things I meant to prepare for. That is. So that is a distance of, you can see the scale on here of 10 kilometers. That is 60 odd kilometers. I can't remember what the height of that bulge is there. It's a few hundred meters, I think. But anyway, you can see what is involved, what we're trying to bend here. And we can see that if a straight line versus the curve of the Earth is almost identical, you can understand the scale of what refraction is required to make a difference between what images you see. Because so one of the claims that I didn't go through there. One of these various claims about things. The main one that they make is that the phenomenon of refraction called looming, which is it rising up, things being more visible but not hiding behind the curve that you think are hiding behind the curve. And one of the claims is that they claim this isn't happening, or refraction is just simply the mirage effect. So they, for instance, will claim that when they talk about refraction, they are talking about things like God damn it. Sorry, oh my God.
Yeah, the comparison.
Yeah, sorry, let me just hold on. Let me just. They think refraction consists of things like Jesus Christ, yeah, I really haven't. I'm trying to. Oh, right, hold on a second. Right, they think refraction. They think refraction consists of things like this and this, which are basically very extreme forms of refraction, and things like this and things like this, that, and for instance, here's an effect which this has got an overlaid of apologies if you've all seen this before, people, but this is a sort of background. Let me just see what this is. One of these is right. So this is the actual image of the CN Tower in Canada, and if we overlay on there the actual Google Earth version of the CN Tower, and you can see that in fact this is a non-linear. This is caused by refraction. I'm going to. God, I've really jumped the gun here. This image here is bloody hell. Right, so what you can see by me overlaying the Google Earth version of this is that this part is not refracted at all, but from here on downwards it's refracted severely to the point that this is all compressed. So this building here, for instance, is this building here, and this tower is here, So even though this bit matches, this area doesn't. It's all being compressed into this point here. That's something called towering, which is slightly some extreme version of looming. Anyway, I just want to quickly, so I'm going to quickly go over what refraction is for people not familiar with it, for the purposes of this. So let me just go up again a bit more to just quickly show what we mean by refractions, the most basic level. And then Phillip will give his analysis of how it affects the... Right, so basically we know about sticking a pencil in some water, and it effectively brings the pencil up. Because it's bent, when you're going from a dense medium to a less dense medium, the light bends in this manner. The angle is increased. The angle, you've got to have an incident angle against the normal to the medium, and that is increased when you go from a dense medium to a less dense medium. So you get this sort of effect here with a pencil seemingly bent, and just due to the fact that the light rays coming from the object change in angle, because and that's determined by the change in the velocity of the light, and that's determined by the density of the medium. The more dense the medium, although Newton got this wrong, the slower the light, the less dense the medium, the faster the light, and that causes, according to Huygens wavefront principle, a change in the angle. Snell's law tells you, there's a law relating to this telling you what the angle of the incident and angle of refraction should be, and at certain angles it sort of internally reflects. But it's all dependent on the speed, the change in the speed of light between the two mediums, and the medium's refractive index determines the speed of light in the mediums, and that's determined generally by the density of the medium. So it is just a little simple example here of what you can do. This is a knife in some water, and oh, brilliant. Why did you? How about just staying there without me having to click on you? Oh, brilliant. Why is that change behavior? Right, so here we remove the water, and so you can see the effect here. That's basically the pencil expression. So I'm removing the water, and so it bends up and down. And you can have some other fun tricks like this. There's this water, if you fill up this glass, because of the particular position of this, it actually changes the direction of the image. Right, so now this is the thing what we're going to be dealing with in practice here, which is the refraction in the atmosphere. And if you consider an object here with emitting light, and this is a model of the sphere here, with a glass layer around it, and this has a refractive index, and the air surrounding this glass has another lower refractive index. And so this Snell's law applies, which I just described up here about the refraction angle. I'll go back to it. You take a normal to the interface of the mediums, and then you get this particular angle. And so an object here, the light actually coming out of this sphere of glass will come off at a refracted angle dependent on the change of velocity. And if you have more layers of here, not just one, but if you have a variety of layers of glass of different reducing refractive index, you get little Snell refraction events at each one of the boundaries, and so you get this sort of effect where each one is refracted following Snell's law at each one of these times, and so you end up with a curving line. And of course, if you have an infinite number of glass layers of infinitely thin, then you get a very smooth line. And so of course the effect of this is that the light, instead of going off on a straight line, actually sort of follows the Earth to some degree, curves around. And so the effect of that is to, oh yes, and here's the atmosphere behaves like that layers of glass. This diagram here shows the the refractive index of the atmosphere is dependent on its density, and that changes with height. So on the left-hand side here, we have the height of the in the atmosphere. This is a table, and here we have along the bottom we have the ratio of against the pressure and density and temperature at the ground level. So as you can see, as we go up, the density, the temperature, and the pressure all decrease. The density, which is the one we're normally interested in, is this red one, follows this sort of curve here. So as you go up, it follows this curve here. And so, for instance, at 2,000 meters up, we're about 0.8 of the density we had at ground level. And so that means this effectively reflects the refractive index of the atmosphere, which changes with height.
Can I interject just for a second? So you'll hear claims by flat earthers that basically when we model refraction in this way, that we're ignoring light bending up versus bending down. And I'd like to point out here that under these conditions, where the index of refraction and the density is decreasing, you will always have light bending down. Because and only time you get light bending up is when you have a gradient in temperature which is opposite to decreasing, so a gradient increasing.
That is an absolutely fantastic point, Philip. Well reminded. I say I'm not functioning very well today, but as you can see from this, there's no possibility of there being any refraction up. The Snell's law that we have up here says that when you go from a dense medium to a less dense medium and the light speeds up, it will bend in this manner. And if the interface, so that's the interface for two mediums here, and if the mediums are arranged as I've done here, these layers of reducing refractive index, you are going to get it bending down. It has no option. There's no plus or minus here. I mean, there's a flat earther who's we're involved in this debate who well, being a flat earther, of course, they don't understand anything at all, just about, and there is no option. Snell's law dictates that it must follow this curve. There's no fiddling around. There's a particular angle, given an angle of incidence, given a particular angle of incidence, you will get a particular angle of refraction, or refracted. The ray will, with a particular angle of incidence, will have a particular refracted angle. That, and it's not going to be one way wiggling around. There's a fixed value, a definite value that it will have, and that means that it, with layers on this something that's synonymous with the atmosphere, you only can have it behaving in one way by default. So it's dependent on the behavior, the layering in the atmosphere. And of course, as Philip was alluding to, if you have inversion layers, if the density is not following this graph that I've got here, that it is at lower levels, particularly when you have a hot sunny day and this not following this curve, this not following this red line. It's saying wiggling up and down here, because at the very bottom here, because these graphs are just concerned with the macro big scale things. They're not concerned with little fiddly bits happening in the bottom 4 or 5 feet. And so it's not going to, so it's going to completely ignore the things that causes the mirages that I was showing you earlier. It's going to follow, this is the sort of the gross effect. And that means that it will only ever curve in one way. But obviously in real life, you get these turbulent inversion layers where in fact you get mirages. But this graph does not deal with any of that. This is the gross situation. And in that situation, you will always get it curving down in the standard case. So, but obviously if you have little hot spots on the ground, or for some reason you have cold air over warm sea or whatever, or vice versa, then this is these very low levels, you're going to have that changed, and then that's going to cause these peculiar effects. And so in fact here I have an example here we have an inversion layer going on, so we're looking through just a few feet of air here, and here we have an inversion layer that's causing the rules to be changed. So basically light, well, we must understand that light does not travel in straight lines in the atmosphere. It just doesn't do it. And just because here we have a case where it's obvious that that's not happening, but unfortunately people like flat earthers think that because they don't understand that you can have intermediate cases where you have the looming effect that we're talking about. This is induces looming, which I should have down here somewhere. Yes. So what practical effect does that have? So for this lighthouse here sitting on the surface of the Earth, having a light beam coming out here and it looming, following the path that I showed you in the with the layers of glass, it will follow this path here rather than a straight line. So from the eye's point of view, when that light ray arrives at the light at your eye assumes obviously the light's coming down in straight lines. It can't do anything else really. And so as far as the eye is concerned, it sees the base of this lighthouse here and not here because it assumes it's coming in a straight line. And so that's following an arc. And there are some various Wikipedia articles which were hopefully Philip will be going into, or a paper on that refraction, which shows what curvature that should have dependent on the conditions. But that's the principle. By default, in the normal standard set of conditions, because the atmosphere is more dense and more refractive at its base than it is at height, and there's a function for that, you're going to get, by default, the light follows the radius of the arc of the Earth to some degree. Now remember from the scale diagram I drew at the top, this is all very, very slight. And for gross effects, things like mirages, this you wouldn't. There's a paper that Philip's going to talk about uses the word negligible. They would regard this effect as negligible because the curvature required to do something like move something by 10, 20 feet over 50 kilometers, they would regard as negligible and not important to their modeling. But for us, when we're worrying about flat Earths and things, and the exact position of things within a few tens of meters, it's actually very substantial. But they mustn't get confused just because a paper has described an effect as negligible. Right. They're talking about negligible in terms of inverting things, moving things up and down in the sky, moving oil tankers up in the air. That's not what we're dealing with here. We're worrying about the small scale effects, and it's not negligible to us. Because, of course, if you wanted to measure the size of something, if you asked someone to give you the size of your house, a surveyor, and they would say, oh, it's 10 meters by whatever. But if someone was trying to measure the size of a molecule to the same resolution as someone might measure your house, they wouldn't regard as a negligible error that the surveyor might have. They'd be much more interested in 10 to the angstroms or something. So to one person in one context, something's negligible, and to someone else in another context, it's not negligible. So the fact that flat earthers can't understand this just amazes me. And of course, this means that with the refraction that we have, things like the sun actually appears in a different position. And in fact, they have to account for this in time and date. They give sunrises and sunsets. Have to allow for the refraction that occurs on the sun so that it matches reality, because the sun is actually further down than you think it. So, for instance, this image here, this sun is actually lower down in real life than it appears to be. And then we've got a little inversion there. They're thrown in for a giggle.
So an interesting comment about that. So basically, because of the refraction, you effectively have more of the Earth, more than half of the Earth being illuminated at any given point. So when people try and reproduce timeanddate.com on a scale model, they will never be able to get exactly what you would see on timeanddate.com, precisely because you're not getting this extra tiny bit of space due to the refraction. So I've seen people kind of try and do this on YouTube, and you have to really think about in terms of this refraction stuff.
Yeah, and also refraction is dependent on the elevation. I mean, I know I've probably brought people up there several times before now, but apologies, but for people who haven't seen this, the refraction is dependent on the angle which you're looking, because it depends. You're going to be looking through more of the well, we'll be dealing with later the equations which describe the what causes the change in the refractive index, and it's what light you're looking through. And the higher your angle you're looking up, the less refraction takes account. So, for instance, we have a graph here showing that if you're looking up an angle of 40 degrees, we're expecting this level of refraction, which is less than 5 arc minutes. But when you start coming to sort of 15 or 10 degrees, things start to change dramatically. And astronomers are very reluctant to use angles of less than 15, although they can actually correct for a lot of this, but they'd rather not, thank you very much. And sailors who are using it to check on stars, for instance, to get their position, latitude, whatever on stars, they don't like looking at stars below about 10 degrees. And there's a fantastic video from Nick West showing how a star approaching the horizon changes its speed. So, for instance, this star here, he took extrapolated from he took, I think, a sample every second or something. I can't remember exactly where this was, how long the samples were, but he then extrapolated from the two samples here, these blue blobs, as to what it would do if it carried on, because obviously the sky rotates around you at a constant velocity until it gets all the stars on it, the things in the sky basically rotate at a constant velocity until they start to approach the horizon. And so the actual position of the star that he was monitoring here, in red, starts to slow down with respect to what it should do if its speed remained constant as it does throughout the rest of the sky. And so here we can see that the elevation, following this graph here, depending on the angle you're looking, the refractive effect is changing. And so as this star approached the horizon, you can see the blue blob is where it should be if it carried on the constant velocity, and the red one is where it actually was. And so actually at this point here, the next one, the blue blob will actually represent its actual physical position, and the red blob is where it actually appears to be. And so on the next step, the actual star will be below the horizon, but the red blob, which you actually see, will be above. Similarly for the sun here. Right, so basically refraction is playing a big role in what you can and cannot see. And as I demonstrated in previous hangouts elsewhere, George Natayuk did an experiment himself, which he showed various refraction interfering. He was trying to do a flat Earth measurement, and he had these various targets that he was looking at, and they're dependent on the weather conditions. The line here would refract up or down above. These crosshairs are being held in a constant position. These targets are moving up and down dependent on the refractive conditions, and you can see they're moving up and down here with respect to this line. And at one point he had to remove those targets, and he was then focusing on this rail on the distance, and he was getting this movement here. So and these subsequent pictures I'm just going to show you, the crosshairs are in the same position each time, and as you can see, this orange thing starts off here, moves up to here, moves up to here, and this represents 10.5 feet. This target is 2.1 miles away. So he's getting a movement of 10.5 feet from where, here in this shot here, where the base is, he's actually had it move from here to here in the process of these photos, 10.5 feet in 2.1 miles, and that represents an angle of 0.43 degrees. The moon is 0.5 degrees, so it's 10% of the size of the moon he was getting, and subsequently he's been doing some experiments in which it's got actually twice that change. Right, so that's what refraction is. So now we need to go on to Philip's side. He's now been trying to model this rather than using, I might go to a Wikipedia page here. There, showing the yellow devil, and there should be a friggin' hell. As you can see, I've prepared for all this. Right, let's get that sorted. Here we go. Right, this is a refraction page on Wikipedia, and it shows what's called the coefficient of refraction, which basically determines the refractive index of the atmosphere. That's not quite the same thing, but it's how it affects the curvature, and it's dependent on the pressure, the temperature, and the temperature gradient. And this gives you what's called the coefficient of refraction, and that can be turned into what is effectively the radius of curvature of the light ray. And as you saw before, I was drawing a line that was curved around the Earth, and this gives you that radius. And so, which is very useful. It means that you can then, it does an approximation, though now Philip's going to demonstrate how you can do that in a much more accurate way. Actually, I suppose is applying this equation. Effectively, you're applying this equation here, aren't you, Philip? But you're doing it for
so
something similar. You're not.
Well,
Okay.
this is empirically derived, and I think the interpretation of this is the effective radius. So it's the effective amount of curvature you're seeing, assuming that light goes in a straight line.
Right, but he does actually describe it here as the actual the angle of the ray. Initially, well, there are two bits of this. Well, one is it. Pardon me. From this actually gives you the radius, I think, of the ray of light for a particular conditions, and that also does that also include its height? Actually, it might not. No, just to
Well, no, it's.
No, I don't think it does. Actually, does it?
I
Actually,
think yeah, it's just giving you the effective radius of the Earth, assuming like basically so that if you plug it into this geometric formula for calculating the horizon distance and stuff like that, it basically allows you to assume that like light rays are moving in straight lines. So like the horizon actually appears as if it was a radius of, you know, this r divided by 1 minus k.
yes. Okay. Well, perhaps we won't concentrate on this then so much. We'll go on to what you're doing. But so the thing, what you're doing, is you're ray tracing. You are following a ray. Well, actually, you might as well. Yeah, probably is best. The idea is that what Philip's done is he's using some similar equations to these. He's actually going to follow a ray from a position on the Isle of Man to the observer. And by following it and then taking into consideration the refractive index of every little bit of air that ray meets, which is dependent on this little yes, actually, is that actually giving you the refractive index?
No, what we need is we need Fermat's principle, because that's what I'm using.
Okay, let's move on to you then, Philip. And
sure thing.
Go into your. So if I present your, so if you want to share a screen or something, I'll present it. So
all right. So should I begin with the paper or?
I think general principle. Yeah. Okay. Perhaps perhaps the paper actually. Yes. Probably that might be.
Yeah. It's got the equations which are necessary. I'm not sure how technical you want me to be, but well, you can stop and ask me questions along the way.
Indeed. All right. So hopefully you're being presented. Hopefully now. So if you grab yes.
Can you see me? It says I'm sharing.
Yes, I can see.
Okay, great. Right. So this is the paper that some flat earthers have gotten a hold of, and in this paper, they are specifically trying to model various effects of refraction, which give you different kinds of mirages. So specifically, it says, this paper presents physically based simulations of atmospheric phenomena. It takes into account the physical, non-homogeneous material in which the index of refraction varies continuously, which creates curved light paths. Okay. And so basically what they do in this paper is they model the atmosphere very accurately, so using real world data. And they get atmospheric profiles which are very different than the one that the Rumpus just presented before. So they're trying to actually get a hold and understand the index of refraction near the surface of the Earth when you might have hot spots and you might have inversion layers. And specifically, they're trying to see if they can model these different types of mirages. So superior, inferior, fata morgana. I've never even heard of this one.
Yeah, and an inferior mirage is one that appears below the image, and a superior one is that appears below it. Mirages, though, technically, as I understand it, they have to be inverted as well. That's the from the etymology of it. But a mirage is an inverted image. So fata morgana is not a mirage, actually.
Yeah.
It's because that is orientated correctly, but it's wiggling around. But it's actually orientated in the right way.
I see. Yes, so there's also another one. So this Vikings end of the world is pretty interesting too, and that's basically an extreme. I think it's kind of this towering effect, but yeah, they don't really call it that here. So basically, when you take the Rumpus talked about this different layers of glass, right, and how it bends light, and you can basically make this statement mathematically formal by talking about what is called Fermat's principle. And so the idea is that I have a path. This equation is basically useless, but I have a path. Right, here we go. And the light ray is moving through this inhomogeneous material. And Fermat's principle states that the light takes the fastest path possible given its initial angle of incidence off of the car. So here you see this is actually a case when the light bends up, and specifically this is the inferior mirage. And so they describe here the exact atmospheric conditions needed to get this effect, where you get this inversion. So you see how when the light bends up, the person actually sees the car underneath the road. And so this happens under very predictable conditions. And this paper actually goes into a lot of detail about what conditions that actually is. And so there's a whole bunch of math associated with this, but in reality, basically, I have from Fermat's principle, I can derive an equation, just like I have an equation which describes the trajectory of a ball, like the projectile motion. I have kind of like an equation which describes the projectile motion of light. And so what my program basically does is it solves this projectile motion problem for light rays coming from the object to the observer. And what I do is I basically I can put in any index of refraction I want, and it will basically calculate this trajectory. And then I use that to render an image. Okay, so here's kind of an example of what the different atmospheric conditions need to be. So I'm going to skip a lot of this. So let's look for the one for an inferior mirage. Okay, so here is the standard atmospheric profile. So this is what the Rumpus was actually talking about earlier. So this line represents the straight, monotonically mirage. The ground temperature is much hotter than the air temperature. And so what you end up getting is you end up getting a profile which looks like this. So you have very warm temperatures near the surface, and then as you go up, that tapers off in an exponential fashion. And if you put your camera in the right position, what you can get is you can get some very weird looking effects. So here they show basically the simulation that they did versus the actual inferior mirage. And of course, the reason why they don't match perfectly is because here it looks like they're assuming basically some uniform temperature profile, but in reality what ends up happening is, you know, if I think about every part in this picture, it might have a slightly different temperature variation, which can affect the actual trajectory.
There will be a temperature variation, of course, because it's there is a gradient anyway. So it is.
There's a gradient this way, but there also might be a gradient this way.
The actual gradient is moving around like crazy. It's not just that there's a change. It's the change in the change. Is weird.
Yeah, exactly. So this curve actually might fluctuate as a function of time. So that's why when you see some photos of astrological photos, right? That might be wiggling. So if you look at the Wikipedia page, I think there's a nice GIF of the moon and how it kind of like wiggles and dances. Or when you open up the door of a car and it's like really cold outside, you see like all sorts of weird effects in the air, which it looks like, you know, kind of wiggles, but that's just because the temperature is changing and the density is changing so fast over such a both time and space. Right. So my concern with my program initially was just trying to understand the standard condition and what it means for observing things very far in the distance. And so what I did was, in particular, looking at the Isle. I was looking at the Isle of Man, and I was first looking at the Mulgold Lighthouse, but then I decided to basically just try and see what the whole Isle of Man looks like. So let's see kind of the, so do you think that's sufficient introduction, Rumpus, or should I mention more about how I do the ray tracing?
I think you have to mention which particular bit, the solving the equation, your ordinary differential equation bit, or do you which part?
Oh
do you
yeah,
think?
yeah. Okay, so let me pull up my notes and I can show you which equation I'm solving for both the flat and the round Earth models. Okay, so I'm going to stop sharing just for a second, and I need to do another screen.
Okay.
Share.
I'm just gonna go. I need to go.
So where are my notes? Notes. Here we go. Oh, it was probably the same application. Okay, so I just did some notes on the atmospheric model. This is a standard. Can you see this actually? Yeah, hopefully you can. So this is the standard equation for a fluid which is under the influence of a gravitational force, right? So this equation right here basically tells you what buoyancy is. So yes, it's a fact that you need to have gravity in order to have a buoyant force to begin with. This is just simple fluid dynamics.
Yes, because as we know, what happens if you go into a non-gravitational situation, as on the ISS, we can see what happens to water, and there is no buoyancy at all involved. If you can do
so in this
like
equation,
blow air into the middle of a water sphere and have strange effects.
Yeah, so basically, if you look at this equation, this tells me the change in pressure as I go up in height, and it's related to the density, and it's related to g, which is the acceleration due to gravity. So if g is 0, then my pressure doesn't actually change with height, which means that there's not more pressure on the bottom than there is on the top, which is the whole origin of the buoyant force to begin with. That's just a side comment.
Yeah, that's a good comment.
And so now this is combined with the ideal gas law. So for any of you who've taken chemistry, it's slightly different because I'm normally there's a volume here and there's a mass here, but I've moved the volume over, so I get mass divided by volume, which is density. And so you see here that these two sets of equations, if I solve for density from the ideal gas law, I get a differential equation for the pressure as a function of height. And this is a very simple equation. You can solve it if you've taken your first year in ordinary differential equations. And it has a form which looks like this. It's a perfectly closed solution. And here, pressure is the initial condition of the pressure. So it's the pressure at some height, which you define as H0. And for the particular temperature profile which we would like to look at, which is linear near the surface of the Earth, this is the pressure as a function of height. Now, in principle, I could put in extra effects here, not just a linear profile, but I can put in these weird atmospheric effects, and I can get a different profile, which my code does. It actually solves this for an arbitrary temperature profile. But we're mostly just going to be concerned with this linear profile. And here, delta T is the lapse rate. So it's how fast the temperature changes with height. And typically, this number is actually very small. It's like 10, it's about 10 to the minus 3. So 1 over 1,000 of the order of 1 over 1,000 per meter. So this is truly a minuscule effect.
But surely in the I thought we were dealing with changes of a few degrees across a few meters or was that just in the naughty cases?
I think it's just well, okay. I have, let me double check. But I think it's quite small.
For the standard condition, standard atmosphere we're talking about with that graph that I was showing with the change in pressure.
Yeah, I think it's like, well, okay. I think you did the calculation too, right? So. Oh shoot, yes, right. Well, anyways, I can double check the number in a minute, but it's calculated from another formula which you use to calculate the lapse rate for moist air. So it can vary fairly significantly with the amount of moisture in the air. But here I'm just going to assume that
But the temperature is the most significant factor, isn't it? It's the temperature gradient that's the most significant factor.
Yes, exactly. So it's not obvious from this equation, but you can see here temperature enters in the exponent. So if you change temperature a lot, because it's in the exponent of the equation, that will make this pressure change quite significantly. While if I look at the pressure itself, right, the pressures, it only depends linearly on the initial pressure.
And you only care about the pressure to get density, presumably.
Right, right. So once I have the pressure, I just, again, plug in back into this equation. So I solve for the density, and I get an equation looks like this.
Wow.
So this is all exact, although I just solved this numerically in my code because it's simpler to have a more generic set of code. And then there's, to get the index of refraction, there's this empirical formula which was derived, I forget the physicist who experimentally verified this, but they talk about it in detail in this paper that has been cited quite often. So let's see.
And you've got the wavelength in there, of course, of light.
Yes, yes. Yeah. So, well, okay. So in my renderings that I'm going to do, I'm basically assuming a wavelength of 50. It's like 500 and something. It's green. It's green wavelength. It's because
that's reasonable. I think that's fair.
It's in the middle. It's not not an extreme value of wavelengths. And now one thing I'm not sure is, does this apply? How far outside the visible spectrum does this apply? Like, does this apply to infrared? Does it apply to microwaves? I have no idea, but so far we're only dealing with the visible spectrum. But similar effects can happen with, let's say, like microwaves. And I think because of the wavelengths of microwaves, the refraction can actually be much more significant. So, you know, again, talking about some other flat Earth misconceptions about how radio signals work, you can actually get very extreme cases of being able to go well beyond the line of sight with refraction effects. Okay, so I have a little bit about Fermat's principle. And so basically, generally speaking, the velocity of the speed of light in a material is given by the speed of light in a vacuum, all that c, divided by the index of refraction. And so I kind of do here a little derivation. So if I want to calculate the time that it takes to get from point A to point B, I integrate this quantity here over the path between A and B. And so ds is basically a differential length element doesn't matter which direction, it's direction independent, it's just the length divided by the instantaneous velocity of the light ray.
Yeah, this is just equivalent to saying that time is equal to speed, the distance divided by speed.
Right, exactly. So time is equal to distance divided by speed, and then I'm summing up a whole bunch of tiny differential versions of distance divided by speed.
Because the velocity is changing as a function of distance.
Right, exactly.
Yeah. So when we're thinking of, we might think of something like time is equal to distance divided by velocity. Well, right. What happens if, you might like to consider people, what happens if over that distance the velocity is changing, jiggling up and down, and you've got to consider each, breaking it down to little infinitely small bits, and then working what those are out and then adding them up. There's no constant velocity, and it's a function of the distance you change. So if you wanted to work out how long it took you, say, to get from London to Oxford or something, and your speed was a function of how far you got between London and Oxford, obviously working out how long it's going to take you is going to require this sort of integral we've got here.
Yes, exactly. Very good explanation.
Thank you very much.
So I take this equation for the velocity. It applies at any given point in space. This is a fixed thing, but this n, the index of refraction, will change as a function of coordinate. So now I'm calling r the position of my light, my photon, if you wish, and this gives me the time. So I'm integrating this index of refraction at a given distance over the length of the curve between A and B. And there's a factor of 1/c here to set the units to be time. But in reality, if I want to minimize this, I don't really care about this factor of c. So I'm going to basically ignore that. Do you want me to talk about calculus of variations.
I think probably that's going a bit far.
Yeah. Okay. Well, anyways, it's a way of minimizing something like this. So there's a mathematical formalism to do that, and using some calculus, you can derive basically an equation. So actually, you do this in you can formulate Newtonian physics in this way as well. Interesting side note. So you can write down a function similar to this one, and then this will actually be Newton's law. This equation right here, it's actually the minimum of some path in the...
Feynman used to get all excited about this, isn't it?
Yeah, exactly. Actually, so it's interesting that you mentioned that. So Fermat's principle is the same as the adding the amplitudes in quantum mechanics. So because of Huygens' principle, this this trajectory is the highest amplitude, has the least amount of interference. Kind of like in quantum mechanics, the classical trajectory is the path, the classical path, which has the least amount of quantum interference. So there's actually a connection between this sort of math in light as well as in quantum mechanics. So interesting side notes. Okay, so this is the equation for our... So now what we're doing is we're moving to, so we're calculating this. This is a general equation, but we want to express it in a particular coordinate system. So I'm going to pick a plane, and for the spherical Earth, I'm going to assume polar coordinates. So I wish I had a plot of polar coordinates, actually. Let me pull up Wikipedia, and I can just do polar coordinates. Yeah, see, I think about this stuff all the time, and I don't. Okay, so where's a good image? Sure, okay, this one works. All right, so let me switch screens just for a second. Okay, so here I'm showing an image of a curve in polar coordinates. So basically I characterize the function that I'm trying to find. The trajectory is characterized by a distance to the origin and the angle with respect to this this point here. So here I have like a weird spirally type thing going out and out. So I think the function here is r of theta equals theta over 2 pi. Sorry, phi. And so you see how it, because the radius is increasing with the angle, right? That's why it's spiraling outward continuously as a function of the angle. So basically, I'm going to consider a cross section of the Earth, right? A cross section of the Earth, and that's going to define my coordinate system for my light ray. So it'll be following kind of an arc over this red line here.
Yes, and this is where this is where I was getting a bit confused about. Normally with ray tracing, what you do is you consider your eye and a window. So for instance, if you wanted to imagine you're looking out of a window in your room or whatever, and then you could say if you took straight lines out from your eye to the window, and then you said, right, now what's going to happen to those light rays that have gone from my eye to a particular part of the window, which we're going to call, which effectively is the screen, and then you would consider those lights going out and then seeing what they hit and what happens to them, what they bend. And Phillip here has got a more general way of doing things, which means just a rather complicated way of using boundary conditions to say, I'm just going to take a point here and a point over there and see how they're related. What's the minimum path, presumably, or the best path between those two?
Right, exactly. Yeah. So I pick my 2 points. So this is, let's call P the point, and this is kind of the ground underneath, but P in principle can be up above the surface of the sphere, somewhere over here, let's say. If you imagine in 3D, it's kind of up above the surface. And then Q is the observer, which also might be somewhere above the surface. The light ray is going to go between P and Q along some curved path. And the distance between these points is going to be determined by kind of this this path
and
on the actual
path,
surface of the Earth.
And the path that is going to pick to go through all those differential equations is the one that's the fastest.
Right. Exactly. So it's going to be exactly the light ray, which would minimize the time between point A and point B, and given the index of refraction above the surface of the Earth. So now my code is
basically you're doing all the basically you're considering the actual path of the ray takes through the atmosphere, and considering every little bit of because of course this gradient, you're only considering this you're considering it's uniform from the ground level upwards, and so you're considering as every little height change that ray occurs, you're then reconsidering what that ray will then do depending on its height and which part of temperature and pressure it's hitting, or which comes together as density, I suppose. And then yes, so each part as it goes up and down relative to the surface of the Earth, you're considering every little change in angle that would occur as a result of the change in the refractive index that ray meets. And so it's a very high. It should be if the Earth was like that uniform in that manner, it would be a perfect rendition,
yes,
and rather better than the sort of effective radius calculations the corrections that we might use that we saw in the Wikipedia thing. This is actually following that. This is actually doing a ray tracing, actually considering the ray and every little bit of light, a refractive bit of air that it's passing through, and seeing the effect of it from the start, from the observer to the object. So Phillip could have an amazingly complicated function in there if he wanted to, but he's actually basically monitoring a ray as it's beginning to its end state all the way, and so he can fiddle around with any of the parameters in between the two, and have presumably you can do everything that they did in that Mirage program if you did.
Oh yeah, exactly.
That Mirage paper, sorry.
Right, exactly. So I haven't really had much time to play around with the Mirage stuff, and thankfully, with our conversation today, Rumpus, I understand kind of my what was going wrong, and hopefully, within a few weeks, if I have time, I'll be able to actually model these mirages very, very accurately.
Well, that'd be fantastic, Philip. That'd be really fantastic. That's quite something. Right.
So basically, the idea is that I know I'm going to pick a set of points on the Isle of Man, and I'm going to calculate the ray from every single one of those points to the observer on the other side of
we must mention orthogonal and perspective.
Yeah, exactly. That's what I was just about to go into.
Okay, go on.
Yeah. So P is going to be the point on the Isle of Man, and Q is going to be the observer. And so what happens is I have a map. I have a set of P's, each with a height above the surface of the Earth. And this height data I've gotten from this shuttle mission. I think it was in '97 or something, or maybe early 2000s.
2000, yes, about 2000. The shuttle.
Yeah, but anyways,
this is the same data that Google Earth uses for their elevation data, which unfortunately, as we know, is a bit dodgy in places. Resolution of 30 plus or minus 30 meters.
Right.
When it gets tricky.
But in the case of what we're actually looking at, I think that the error actually gets better as you go up, because there's less atmospheric effects. I think I read a little bit about the actual collection. So the stuff that we're interested in is really the tops of the Isle of Man, the peaks and stuff.
Though you are trying to you're trying to model exactly the position of Morgold Lighthouse, and I think
I did too. Yes.
Yeah.
Yes.
So we're going to get that exactly right, aren't we?
I did that using a different set of data. So the height data for the Isle of Man was not taken from Google, or from this data set. But yeah, so that one I did a kind of a rough estimate to try and figure out how high the lighthouse was. But anyways, so I have a set of P's, which are the points on the Isle of Man, and I'm just taking the resolution to be that of the data set that I downloaded. And so what I do is for every single point, there is a great circle that goes between the latitude and longitude on the sphere to the latitude and longitude of the observer. And I calculate the surface, the great circle distance, and the heading. So for each point, I know the angle at which it comes into the camera from the heading, and the angle of incidence on the vertical from the trajectory of the light ray. And so from that, I can create an image. And this is where my understanding of photography and the jargon that is used there is kind of eluded me. But the Rumpus was able to explain to me that I'm using what is called, I'm using perspective. And this is exactly, I mean, this was my natural thought when I was dealing with ray tracing, because you know the angle of incidence on the object, the sensor that's receiving the data, basically. And so that's why I programmed it this way, because this is kind of the so
it should exactly emulate. So in other words, we should get exactly, using your algorithms here, we should get exactly the same effect as an observer, say at St. Bees, looking at the Isle of Man. We should get exactly the same. If we pick on a particular field of view of the camera on your program, we should get the same results that a camera has. And it's
Precisely.
not like an orthographic view that an architect might generate as a sort of theoretical view of what it looks like from an infinite distance. Oh no, we're getting exactly what you should see from an observer, and
right.
what a camera would have of the image. They should be completely
right, and which is why as we'll show, the images basically match up perfectly with what was taken. Okay, so you think that's pretty much it for the introduction? I think
sounds good.
Okay, great. And obviously, one thing, yeah, I think if you want Rumpus, I sent you that link, right? You can put the link to the code in the Google yeah, I'm perfectly fine with sharing that. So yeah, when this thing is done, you can put that in there. People can download the code and try. I'm warning you though, it's not commented.
Yeah, it's a bit deadly.
It's probably going to be pretty hard to read. But don't inundate me with questions. But if I don't respond to a question, then don't take it personally. I'm trying. I'll try my best.
Yeah, I think you'll find it might take a bit of time before that happens, before they start to digest. Anybody digests it. You'll probably find over the next few years or something, you'll probably get one every month or something, perhaps.
Okay. So now let's go on to the results, the final results. Okay. So I need to open up. Oh man, I have so many images. All right, so let's just start with the positive results, just to be clear. Okay, Google. Stop sharing. And let's do this. Great. All right. So can you see this?
Yep.
Awesome. So here's so this is my prediction for the globe model. And what I have here is the dots are colored from yellow to kind of a bluish color. It's hard to see here. And that's to indicate kind of the distance away from the camera. So for example, this guy is a little bit farther away because it's slightly more green, while this point is close.
Yes, so let's just remember how we got this data. You've generated a mesh, haven't you, from
yes. So you see these little dots here, right? These are the actual like points of data for height information on the Isle of Man. So you can even kind of see the mesh.
And then you've just coloured it depending on distance, gradually from yellow to, so we can actually see the other side of the mountain there. We can see through the holes.
Yeah, exactly. So I rendered every single point, whether it goes through land or not. So that's why there's like a whole mess of points. And yeah, you can even see all the way back to like the other side of the Isle of Man. So interestingly, what I did was, if it's below the horizon, so I can tell when it goes through the surface of the Earth in my program, I'm coloring that red to be hidden. So this is something that is hidden. So this is nice because you can actually see kind of how much of the Isle of Man is actually missing from this photo due to the curvature of the Earth. It's quite remarkable. Another note here is that you'll make this later. this hill right here, it's called North Barul. It's actually, my prediction is that it's going to be a little bit higher than the largest hill, Snaefell, which should already give you a little bit of an indication, because this is the tallest peak, and this is I think it's like maybe the second or third tallest peak, and yet it's higher in this image. In my rendering, it's very interesting. And again, just to bring up some claims. So there have been claims by flat earthers that this land here should not be seen. And well, according to my simulations, it's perfectly well to be seen. It's right there. Okay, so let's compare it to the actual composite itself. So here you can kind of see the land that's poking up behind the horizon over here. Looks pretty much in the right location. Then we have this bit coming up and this little mound here. And then
the black outline, where did that come from?
Oh, this? Oh, I think I was trying to calculate some distances, angles.
No, the black outline round the Isle of Man, not down.
Oh, I put this in for emphasis.
Oh, right, okay, right.
Of the actual, yeah. Oh, yeah. Sorry. So yeah, because it was really hard to make out the actual where the land is. Yeah. So you can kind of see it's. I can show you the raw images.
That's fine. That's
so the peaks are hidden in this image, but we'll go back to one and we can actually explore what's going on up here. But for now, let's just see the overall outline. And it looks like it matches pretty well. And so what I did was I decided to just overlay them. And basically, if you look, you can kind of zoom in. It's not exactly perfect, but the horizon matches up fairly well. And the profile matches up fairly well too, except for around this point. And so what's happening here is that this horizon, the person who made this composite didn't realize it when they were doing it, but this horizon's actually kind of bending up.
Yeah, I mean, as I said earlier to you, that I've got a corrected version of that, and you wouldn't have that problem if I'd got to the correct composite. Yes, which is accounted for down here. Yes, so
yeah. So what I did was I just took this image, cropped it out, and then copied it, and then overlaid it so it's a snug fit, and it works perfectly. And the same thing with the land over here. So. So there's an interesting little artifact here. So I think there's a little bit of land poking up, but this is so close to this very low lying atmosphere. I think there might actually be some of this miraging effect that might be hiding this.
Yeah.
But I mean, I think for anything above this line here, which is, I think you can even, I've kind of cut it off here, but there's a little bit of miraging that's happening right here. But anything above that is not being affected by the inversion layer.
Yeah.
So yeah, so it matches very well. So now
this is for spherical Earth, and what refraction have we got here?
Oh, so this is, oh yeah, so I looked up the conditions at St. Bees. So I can put in the temperature and pressure. So I literally went up and found the temperature and pressure around near the time when this image was taken. And I inputted those into my calculator to get the amount of refraction. So it's literally, the height was measured by the people there. The temperature was measured by a weather station nearby. The pressure was measured by a weather station. So everything that I put in is completely independent, uncorrelated data, just related to the atmospheric conditions. And then the rest is just the prediction from Fermat.
How did you get a temperature gradient for? Did you have different heights for? Did you have
no? So I applied this formula. If you look at lapse rate on Wikipedia, they talk about a more complicated way of deriving the lapse rate, making some assumptions about the amount of humidity in the air, basically. But I think it's a little bit more accurate than just using the standard value, which is like 0.006 degrees per meter or something like that.
So this was effectively with a refraction. Oh wait, no, wait, you use the atmosphere. So what did your atmospheric conditions bring the equivalent, what we call the Did you look?
Yes,
Does
I
it make any
calculated this
sense?
effective R.
Yes. Does this actually, because you're considering? Yes. Can you calculate an
I
effective
did,
R from
yes.
your?
Well, assuming I did it correctly, so maybe I need to go back and read this again, this article, Wikipedia article about it. But I'm assuming it's you take the ray coming from the horizon, and then the angle, let's see. So then you take that ray that comes into the observer at a particular height, and then you project that out to infinity, and you assume that there's no refraction at all, and you say, okay, given that is where the horizon is from my line of sight, my refracted line of sight, then you ask, what is the radius of curvature of the Earth, assuming that light goes in a straight line? So that's basically what I calculated.
Right. Okay.
I should draw a picture.
Yeah, perhaps we'll talk about that some later time. But you ended up with a value of what, 1.3 or something, didn't you say?
Yes, exactly, 1.31.
Right. And so the standard is 1.16.
Yes. And interestingly enough, it's maybe there's so that value of 1.16, I guess, is supposedly coming from observations over land.
Yes, absolutely. This is it.
So there you have to be a little bit careful about the effects of this inversion layer. So the inversion layer can actually make this value actually smaller than it would under standard conditions, as far as I can tell, because basically, well, okay, it can make it either much smaller or much larger, depending on the temperature of the ground. But over water, I guess this can be, this seems to be a typical value. I should look up for some citations to make sure this is consistent, but.
Yes, I mean, it does seem that I think 1.3 would be regarded as medium, if not slightly above medium refraction conditions. I think we need to, investigate exactly how you're calculating that.
Yeah, I might be calculating it wrong. Okay, so we can
because you see, if I used when I was matching positions and I was using an effective radius, I found that I could account for almost everything within a few meters with very close to the standard. And it was only with the Moorgold lighthouse I had to up the refraction to count for. It was wrong by about 7 meters or something. Not very much, but enough to think I could do with upping it a bit. So I'm a bit surprised it's quite so high that you're required. So it sounds though possibly there's some sort of mismatch there between concepts.
Using that value, the atmospheric modeling that I did, Moorgold Lighthouse matches like really well with what was observed.
Well, of course. And of course, the thing is, you're modeling this much more accurately than just using an effective radius thing. As I was saying earlier, you're actually modeling each little ray, going through each little temperature gradient, and so yours should be much more accurate. So yes, you could have that higher refraction, and of course, as we were saying before, as I was describing before about the elevation, the top of Snaefell is an angle of 0.5 degrees. I can't remember that. Damn it, my graph, what it was in the arc minutes. But yes, we're obviously getting a lot less refraction of the top, and so of course, hopefully later you're going to show us the comparison of the non-refracted and the refracted case of these two, so we can see exactly what refraction does to the image.
Yes, exactly. I do have those. So this is
the 1.3. So effectively, we're looking here at a 1.3, and it's matching the composite exactly.
Yes.
Right. On a spherical Earth, of course.
Yes, on a spherical Earth. So I can model the standard refraction also on a flat Earth. But typically speaking, from what I've done, it doesn't make too much of a difference. It will change kind of the positions, but very slightly. It doesn't really. So the thing about this is it doesn't. It preserves the scaling of the image fairly well. So points between, if I look at like basically the image is not distorted very much at all. Like there might be some distortion near the horizon, but it's really, even that is like, it's very, very, very small. in terms of the proportions of the thing. So like, because the change is so gradual, right? If something's very small, then it will always keep the same proportion.
And of course, the thing that's people may remember, some called Nathan Oakley and others, this flat earther contingent, they get the idea that when we talk about these refraction effects and the looming, as I was describing earlier, they get some idea that it's jumping up and down by, you know, half the size of the image, but it's not. It's just moving up by just a few pixels up and down, and there's a slightly non-linearity, which means the top is quite close. Well, perhaps we'll see an image finally later. The difference is very small top, and it's just slightly more at the bottom.
It also depends on how far away the point is away from you. So you'll get more refraction for things farther away than you do for things which are closer.
Right. Yes.
Yes. So it's actually a fairly complicated thing.
Yes, because that wouldn't be. Oh, no, that would be included. The effective radius thing would get that right, actually.
Yeah. Exactly.
Yeah. Okay.
Because it has more time to go through the atmosphere, and so what happens is it gets bent more. It tries to go up higher the farther back you are, because it's trying to use the fact that the index of refraction is lower at a higher elevation. So the farther away it is, the farther up in the image it will go.
Right, because it's got longer to refract, right? Yes.
Exactly. Yeah, basically.
The distance over which it travels also greater, which means that because this is an angular effect, I mean, ultimately, if we were looking at something, you know, many millions of miles away, the actual physical distance in terms of meters would obviously be huge.
Mm-hmm. So and the only effects would really happen once it got close to the surface of the Earth. So effectively, for all starlight, they're getting the same amount of refraction.
Right.
Okay, so now what? Should we do the flat Earth?
Whichever you got the order. So what we'd like to see, I think, is a comparison for the spherical Earth of the refracted and non-refracted cases, and then of course you want to look at the flat Earth conditions and see how that compares to the composite.
Yes. So let me do the non-refracted case. Did I stop? Oh, I did stop sharing. Okay, good. Smarter than me.
Oh, have you put in the where the zero is? Because of course, one thing I forgot to mention where Nathan claims that the flat Earth. Because hopefully, you've got that. Okay, great. Because we want
it's for the same. It's for the same rendering as before. So let me just pull it up and show you. And yeah, someone should actually do a theodolite and show that's where it is.
So yeah, so we're talking here about where is the tangent. So if you're an observer standing on the ground, we now want to consider what is 0 degree, what is horizontal from the observer's point, and where does that hit the target? And great, you've put it in, excellent.
Yeah, so this dotted line is 0, and if you don't believe me, I put in the actual scales here. So this is angle and radians. So this line goes all the way. I mean, I guess I should have put it all the way here, but
that's fine. And also you get the same line in Peak Finder, and it's one I've been meaning to add to the composites as well to show, because I haven't been making clear when I've been doing
it's the same with Peak Finder. Okay, that's good.
Yeah, that agrees with Peak Finder. It agrees also with the angle I've done as well when I've calculated where that should be. That's in the correct place. So yes, you've got that. At least I must admit I haven't checked yours, obviously, but that looks about right. So I think on the sort of first thing, and that's also where Peak Finder suggests it should be as well. So I think that's right. So that the dotted line there is the that's, in other words, that's the drop you can see there that's occurred as a result of the curvature of the Earth, and then been brought up a little bit by refraction. But obviously, the most of the effect, it's not going to completely compensate for the drop, as in the layman's drop. Well, I suppose the technical one as well. That's how much the Earth has descended at that point there, and it's dropped by that amount, which of course wouldn't happen on a flat Earth.
Yes. So I should have. Oh, I wish I would have thought of this. I should have done it this 0 line for the flat Earth too. Because
didn't you do that? Oh, right.
No, I forgot.
Well, that's fine, because it should occur right on the. It should occur on the horizon.
Well, it's actually going to occur slightly above where the Isle of Man's shore is, because the Isle of Man's shore is not infinitely far away.
Right.
It's actually going. So yeah, that's the subtlety, because the 0 point only happens. So if you're at a height, right? It's and if you're above sea level.
Right? Oh, right. Yeah,
flat Earth, you have to look down to the shore on the other side.
Right.
So the horizon's not actually at eye level.
Oh, right. Yeah.
Oh,
But
sorry, the shore is not at eye level.
yeah,
It's
yeah. But when sure. Hold on. So what's this line for? Is that not for the tangent to the Earth's surface,
this
or you
one.
join?
This one is, yes.
Ah, right.
But on
Yeah.
a
So,
flat Earth, I would have to put like a line at 0 degrees, which would be parallel to the observer, right?
but surely on a flat Earth that would go through the. Well, it would go through what? Well, the zero. The zero. Surely we're
No, because
matching. We're going
the
along the
beach
plane.
is
Surely, why would it be? Why would it not be at the bottom? Because obviously we're missing some of the Isle of Man and your image here. But on the flat Earth, surely it would hit the shoreline of the Isle of Man, wouldn't it?
yes, but
It's
it
the
wouldn't hit exactly at the shoreline because the observer is not infinitely far away. So if you think about like a triangle, like the observer has to look slightly down to the shore
right.
because
Yes.
they're at a finite height.
Yes, I suppose. Of course, this is the viewers. Yes, okay. So the image, you're okay. So the composite image. Yes, I suppose you are. You're right. Okay. Yes. Yes. Okay. So you are
Yeah, just
looking down
imagine the
slightly.
observer at some 10 feet. I mean, it's almost 0, but
What
it's
height?
not
What height
exactly
is it? What
0.
height? You're modeling this at what height? By the way.
29.6 meters.
Right. So that's close to the second obs. Right. That's for the composition. Yes.
This
Okay. So
is,
that's
yes,
slightly below where he actually was because
right.
it's 35 meters was his actual position above the water. Yes. So of course you've got to be careful about allowing for tides and
So,
things.
right. So, right. So, yeah, there's a lot of questions about like heights and stuff. And,
Well, we've established it's at
but this
35
is,
meters for the
right.
composite he took. We've established it's 35 meters.
So then, I mean, I think I actually haven't done, I think I did one for 33 meters, but I think I don't have the data anymore. But that's only going to really change where this horizon is very slightly. And since we're not interested in the actual objects near the horizon, it's not really going to make too much of a difference.
Yeah, not yeah.
It might make a few feet.
Yeah, it'll move. Yeah, I mean, so if we're talking about Morgold Lighthouse, it would make that change by
Yes.
about 10 meters. So that would make quite a big difference in Morgold Lighthouse.
Right. Okay, so let's go to the flat Earth version of this image, and
Have you done it without refraction here?
I have one. Oh yes, yes, Isle of Man 29.6, no refraction. Compare. Okay, yes.
Oh, it's a compare. This would be so. This is the image I wanted to present. I meant to do got some weeks ago to in my presentation about showing what the refracted case and the non-refracted. Pardon me. Holy goodness, cases are to show you what is refraction actually doing to what you can see, what you're seeing.
I wish I could show both images simultaneously, but
oh right, that's what I was. Yes, if I hadn't been feeling so poorly, I would have. Yes, I'd have got these images from you, then done a transparency thing on them to merge them together.
But you can see if I switch back and forth, I think I can just do the windows.
Okay.
So here's the non-refracted version, and I specifically pay attention to how much of the horizon is hidden. Okay, so can you see, did I switch? So this is the, oh wait, no, this is the one with the level. Sorry, let me show you the, sorry about this, guys.
That's all right. You're doing fine, Philip.
Okay. So presumably it's showing my image viewer every time I open it up, right?
Yes, it's showing one of your window. Yes, if you've got the same, if it's in the same window, it'll keep on showing whatever's in that window.
Okay.
So if you change what's in that window, then it will carry on. So if you
is it presenting?
Not yes, you're.
Oh,
yeah.
It's not. Okay.
Oh, you've switched it off. Yes, you've said you've switched off presentation.
Oh, I see.
I'm still presenting you, but you're at least I think yes, that's right. Yeah.
Okay.
Now. Yeah.
So here's the non-refracted case. Or sorry, the refracted case. And then now tell me if I switch, the images change when I do this.
No.
No. When I do this, did it change?
Nope.
Oh, okay, this is gonna be obnoxious because I have to. I wonder if I can open up another one. Open. No, okay.
Okay, well, should we leave it then? It would be
Well,
nice to see
the point is simple. So let me look at Google and see what it.
Perhaps I'll tack something onto it.
So the point is that the refraction actually changes the relative height of Borul and Snæfell.
Oh, does it?
By a noticeable amount. Yes.
Oh, right.
So I'm showing it right now, I think. So you can see that Borul is even more higher than it was in the other image.
Right, because in the composite, the actual image we see from the 35 meters, North Borul is actually slightly higher than Snæfell.
Right, but here it's more pronounced. So
right,
I'm actually currently showing the how is it? Maybe I'm not showing the right one. All right, I will get this, guys. I promise.
Of course, in idiot Chris Monk's 3D model, of course, it bears no relation to anything because he's got on the his flat Earth thing. That's the other thing we must emphasise that when Nathan, who most people probably watching this are familiar with, claimed that you had confirmed that it was compatible with the flat Earth, this is actually what you're demonstrating is not the case. What you've shown is that this is you're invalidating the flat Earth because the images you create are
not consistent,
different to the flat Earth.
Yes. So point out here, this is no refraction on a sphere Earth, and notice how Snæfell, which is the highest mountain on the Isle of Man, appears to be lower than North Borul, which is not the highest mountain on the Isle of Man. So this is fairly important. So this is with no refraction. If I show the one with refraction.
Yeah, I think Snæfell's a good 5 miles or something like that behind North Borul.
Yeah, exactly. So it's a little bit higher. Now, it's not much higher, but it's still below North Borul. But the refraction kind of brought it up a little bit, and this is because the light has more time to get refracted since it's farther away. But still, nonetheless, it's still below.
That reminds me. I must remember.
Now let's go.
Sorry, I'm just reminding myself that I must show the Chris Monk thing where he shows, in fact, Snæfell being above.
I'm going to show all the peaks for both round Earth and flat Earth predictions. So it'll be there, yeah.
Okay.
So let's go and now open up. Okay, so let's go. So this is the 20-meter observation, right? The second image. It's around 20 meters, right? I think.
Sorry, I was just.
Sorry, the first observation.
You're not presenting.
Oh no, I know. I'm just trying to find the right one.
Okay. I'm just trying to.
No, this is flat. Come on.
I've got to find that. I've got to find that Chris Monk abomination. Because you're not going to actually show Chris Monk's effort, are you? You're going to show yours, and I must make sure while we're here, we invalidate that idiot Chris Monk's attempts to doing this. Oh my God! And he claims his model is his idea that his model matches the composite. I mean, even the most basic attempt at doing so, it shows it disagrees. I mean, this guy is an absolute idiot of the first order. Oh.
Okay, so I'm presenting basically the composite now at a different height. So this is the same height as what the pictures are taken, and I've overlaid my modeling versus the actual image. It's kind of hard to see because I didn't do that outlining, but I mean, it's hard to see because it matches exactly.
Yeah.
And you see this hill, Snæfell, at this angle is not as far. It's actually almost close to equal to the value of North Borul. And this is partially due to two things. So there's refraction, and there's also a change in perspective because I've changed height, which means the relative angles between the two peaks have also changed.
Oh, what height have you changed to?
20 meters.
Oh, right, you've gone down. Okay.
Yes.
Right. That's actually that. Okay. What you've done is moved down to where his first.
Which I think this is where this picture was taken, right?
No, that picture was taken in the second height, the 35-meter position. The composite was taken from the 35-meter height.
But this is not. This is not cloudy.
Oh, that's a good point.
Yeah, I think this is the first observation because it's very.
You're absolutely right. That's not the cloudy one, is it? You're absolutely right.
Yeah.
Good point. Yes. Okay. I don't know where you got that. Oh, did you do a screen? Did you do a screen grab on that, or is that another?
No, that's the one that you sent me, right? This is the one that you sent me the other day.
Ah.
So unless he did 2 observations at the higher points, I thought he only did.
He did do 2 at the. Oh no, this one I sent to you was one that Al K had done. He did it at 20 meters. Yes, sorry.
Oh, perfect. Okay.
This is yes. Al K who went there. He took some pictures, but it was very hazy, and
right.
but he did it from 20, about somewhere between 15 and 20. Yeah, no, sorry, about 20 meters. He did it from a place called the car park next to the hotel, what's called or tarmac area next to the cafe. And that we've established, I think, is at, oh, sorry, it's near 15 meters. Sorry, 15 meters is where that.
Do we know the tide, though?
When he did it, no, I don't know what the tide was doing. I think it was a high tide. Yeah, I think when he did it, it was, oh, God, he did it several shots. I don't know, unfortunately. But it's about 15 meters, not 20. So you would expect to see... yeah, so if you've put it in as 20, you would see more. Yeah, okay, oh, God knows what. Yes.
Well, okay, we'll have to find a different image then to use, I guess, because this is the exact height that I so it's the exact, well, actually, wait, no, because you have to take into account the tide height as well.
Oh no, sorry, no. Oh God, no, take it back. No, that's right. This is sorry, this was one from 22 meters. That's right. Oh God, get confused with the sunset shot. Yes, Al took this one. That's what I told. Yes, this is taken from 20 meters. Yes, 22 meters. Sorry, this is taken from the first observation height. Yes, that's what I said. Yes, God, sorry. Yes, he went back.
Riley's first observation.
Yes, so this is from the first video, not the composite. Yes.
Okay, great.
Right.
Okay, great.
Sorry. I told you. Yes,
that's why I did 20 meters because
that's right. Yeah, I remember telling you now. Sorry about that. Yes. It's because I got confused about what image you were looking at. Right. Got yeah.
Oh, it's really hard to tell. Yeah.
Yeah, it's from 20 meters. Sorry.
Right. So let's open up. Now let's do non-refracted version of the flat Earth because we haven't done any flat Earth stuff yet.
Let's do some flat Earth stuff. Yep.
Okay. So this is the case where you can make a very, very clear comparison. So, and this is related to Chris Monk's mistake. So I do application flat, right. So you can see a clear difference between the 2 peaks, and the deviation is actually quite large. So, so I tried my best to try and get the aspect
this looks ratio like this. No, his was even worse, wasn't it? He, in the Chris Monk, which I'm going to pitch up in a second, the Snaefell was quite a bit higher than. Yes, I suppose actually that's okay. Sorry, that is. Yes, I suppose that is quite close to what Chris Monk has, isn't it? Actually.
Yeah, exactly.
Yeah, sorry. Yeah, so that's this Chris Monk one had the Snaefell being quite a bit higher than thingy. Yes, I think it was. I thought it was even more than that. Okay, Karen. Yeah, sorry.
Well, maybe it's more.
I'll try and get the picture.
Yeah. So my next project is to try and make this a lot more systematic. The method of actually doing this matching. So the problem is because there's no horizon here and I don't know where to put it, because there's no, flat Earth model for where the horizon is, I kind of just have to guess and, try and place things where they should be. So it's a bit of a guessing game.
Right. So the point is that this is the flat Earth model with no refraction, and we're getting Snaefell being higher than North Barrule, whereas in fact in real life, North Barrule is higher than Snaefell. So we have a contradiction here with the flat Earth model and reality.
Yes.
and not what Nathan claims, which was that it's compatible. He keeps on claiming that the flat Earth model gives the right results if you don't have to make any allowances. You see what you see, but you don't see what you should see in this. You see exactly what you shouldn't see. It's with the spherical Earth model you see what you should see, and with the flat Earth model you end up with this, which is not what you see. It's not compatible with reality.
There's two things. There's the peaks and there's the horizon, which are both wrong.
Yeah.
There's no explanation as to what this may be. And any notion of somehow having an inversion layer, which has to invert, remember, inversion layers have to reflect things from above to below. And there's nothing that's colored water above the inversion layer. So there's no way you're getting a watercolored mirage, which is hiding the bottom of the land, because there's nothing watercolored above the water.
No.
And this is the thing that all of these flat earthers fail to realize, is because literally it's an inversion layer. Things get mirrored from above.
Yeah.
So if anything, I should see the water up here, not down below, because things get reflected up, not down. But anyways, that's besides the point.
And so you didn't bother. Yeah, there was not very much point doing one that's got refraction.
Well, I did one with refraction.
Okay.
So I can show you it. It's very flat, 20 meters, and it's almost identical. But just to prove it to the rest of the world, boom, it's exactly the same. In fact, it might even be a little bit worse. I don't know. So yeah.
Right. And while you're there, I'll just switch to my Chris Monk appalling effort. Can you use my screen?
Yep, I see you.
Right.
Oh wow, that's so far off.
Yes, that's right. So here is the whoops. Oops, sorry.
Oh, I think he's.
Sorry, I've rephrased. I've rescaled the wrong thing. So right. So here is here is his model with Snæfell here and North Brolly, as well as being the shape being wrong. And of course, he's got these extra bits in that shouldn't be there because, of course, he has. He was trying to disguise them in his demonstration. He was positioning. He was. I don't know if you've seen it, but you I think it says you actually have.
I've seen
he
it,
moves
yeah.
the composite, the bitmap he's got, and he actually uses it to obscure rather inconvenient bits of mountains in the distance that you should be able to see on a flat Earth, but you can't on a spherical Earth because, of course, they've dropped further behind the curve, and therefore you don't see them. So you don't see these things to the left. And of course, you don't get the drop on Snæfell with curvature, which you do in real life. And of course, so down here, North Barul is actually above Snæfell, but of course, on the flat Earth model, because there's no additional drop due to the distance away from you, Snæfell is higher in his model than it is on Snæfell. So even, I mean, these are the two biggest peaks on the goddamn image. And I mean, if he's going to say that the reality matches his model, he didn't even bother to check the two biggest features on the model and then compare them. The guy is an imbecile. Though I suppose I got it in the composite. I suppose I got him some mitigation in the fact that it was cloudy. But if he bothered to go and investigate like I've done here, I've got another image of the two things, the two peaks on another picture. The North Barul is higher than Snæfell, and as we've seen subsequently in other images, they are. But if you just choose the composite, there is a bit of cloud there, I suppose. Yeah. But the point is, he didn't. Just like all flat earthers, it did not bother to check the results of what he was modelling against reality. And so you end up with this ridiculous point. You immediately look at it and think this is bollocks, as well as the fact it's got mountains that you can't see appearing because, of course, there's no curvature in this, and therefore things further away are higher up in effect with regard to the observer. So you can see them in the model and you can't see them in real life. And things that are further away should be lower, and they're not. So they appear out of shape, and the shape is wrong. The relative positions are wrong. The heights are wrong. The whole thing is a disaster and does not match reality. So how the hell this idiot can claim it does, and then Nathan, of course, who's not really interested in whether something's true or not, just simply says Monk said it's matches reality and therefore calls it a perfect match. These people do not check anything they ever say or do. They just simply want to believe what they want to believe. Oh, and when here we got and he contrasting with what Philip's doing and what I try to do as well.
So yeah. I'd like to point out there's one particular value where the peaks will line up, and it depends. It's very special because it's, like I said before, it's because you have two triangles, right? There's a magical height where if you're just at the right height, it'll match up perfectly. And so, but you know, you can do this observation over and over and over again from different heights, and you see that the peaks are basically the same height. And if you do that on a flat Earth, because of perspective, the heights, the relative heights will actually change pretty dramatically.
Right. So is there anything else you had there for us? Or did I stop you actually in the middle of something there, or do you come to an end of your bit?
No, I mean, I can show like comparison of the composites.
Oh yeah, yeah, that's good. Yeah, we like that. Any comparison photographs are.
Yeah, let's
good.
do another.
Okay, I'll
comparison.
I'll present to you.
Okay.
Oops.
It's the same sort of thing, but I'll show exactly like those peaks in which that should be hidden, but are not because the Earth is. Sorry, peaks that we don't see, but according to the flat Earth model, should be there. So let me do this. Okay, so I'm sharing now.
Yep. Yeah, we can see you.
Okay, so here's the same sort of thing. Again, where's the horizon? It's definitely not down here. It's up here, according to reality. And so I've tried my best to match the image, but it's significantly harder with the flat Earth model. For obvious reasons.
And there's that little mountain peak. I like that little mountain, the right left hand side.
Yeah, exactly. So this is not a part of the image, right? That's why I put the line in there to highlight it. Similarly with this part here, I mean, of course, this is incredibly difficult to match up, but you can tell just from looking at the outlines that there's no way that these are going to match, even if I try and move this line down slightly to account for this change in the this curving of the horizon.
Yeah, Rad's a special trick there.
Yeah, exactly. Because like look at how high this peak is compared to the actual peak in the composite. And this is because, again, this peak is farther behind the curvature of the Earth. And so it should appear lower relative to the stuff in the foreground. Yeah, and this is one with refraction. But like I said, the refraction makes little to no difference.
Yeah, because I was describing earlier, on a flat Earth, of course, you're only going to get refraction when your light ray hits the medium change at an angle. Because I think I was describing to you, you slightly corrected me, I think, but if you imagined you were looking at those glass layers that I described earlier of the Earth, and you were looking along, imagine that Earth was instead flat, and you were looking, even if you were looking, say, at layers of ice or layers of glass stuck on. Yeah, flat plates of glass stuck on top of one another of different refractive index. If you're looking along them, you wouldn't get refraction, and that affects to some degree what's happening on the flat Earth, because you're looking along, because the refractive index changes vertically, because the density changes vertically. You're almost looking along the layers, and if you're doing that, you're not going to get the refraction. Though I think you said because the angles are slightly curved, you're still going to get some.
Yes, if I can actually go and so these are all images of what the camera should see, but I can also show some side, like kind of cuts showing the trajectories.
Oh yes, want to see that.
That might be kind of neat for people to check out.
Definitely.
I can show what standard refraction does and why it's not negligible, and what do we mean by actually showing something is negligible. So let's see. So I made a Jupyter notebook. So here's just kind of my my great artiste inside, trying to show what happens when you have heavy amounts of distortion. So you see these are the actual positions of the original light rays, but because of refraction, you can get a highly distorted image. So this is what you'd actually see. All of the proportions are wrong because the way these light rays get bent. And in some cases, you can even get mirroring effects because two light rays get bent in such a way that the object can appear in two locations at once.
Yes. Right.
So what I did was this is just flat Earth model, and it's showing the effects of standard refraction over very long distances, and it's actually very similar to what happens on the Earth. So this is the slight amount of refraction that you get, and it's obviously accentuated a lot because look, this is 16,000, and I'm terrible because I didn't put my units in, but everything should be in meters here.
Right, so 16K.
My advisor would be yelling at me right now for not getting that correct. But basically, I can compare the proportions of the angles of incidence, which tell me my eye how high something appears.
So what's the left side? What's the left side?
This is the camera, kind of like where the location
what are the units on the left-hand side? What's that showing?
This one?
That's meters as well, is it?
Yeah, everything is going to be in meters.
Right. So we're looking at a cross section of. Oh, right. So we're looking at a ray, but that's not to scale, though, surely, is it?
No, it's not to scale at all. Yeah, this is completely not to scale.
Yeah, sorry. Of course,
none of these images will be to scale.
Sorry, of course. Yes, of course, you've done that by the meter. Sorry, yes, that was a silly question. You've shown.
No, it's okay. It's fine. So yeah, you can see here's the Earth's surface. It's the blue line, and then we have three rays from the middle, some point in the middle, some point in the bottom, some point in the top. And here I'm plotting ratios of this height, the distance between here and here, and the distance between here and here, divided by the total height. So I picked it such that this is 2/3 and this is 1/3 of the entire object. And so I can compare that to the angles here. And so the angles, so this is the actual ratios, 0.6666, 0.3333. And then here's the angles coming from the ratios coming from the light. So this is the ratio in the image. And you see it's negligible. It's 10 to the -7 and 10 to the -9. It's as negligible as you could possibly imagine. So this is what is actually negligible. The amount of distortion, so the amount of change in the object's actual appearance when the light rays get bent. And this is accentuating how much refraction there actually is. I mean, it's actually very, very, very small amount. And it's so small that it keeps the proportions exactly correct.
Right.
Do you want to just go through Mogul Lighthouse?
Yeah, why not? Yeah, I think people would like that, yes.
So I took this image, and the distance that we know is the distance from mean sea level to the focal height of the lighthouse, which the focal height is where the light actually is.
Oh, God, yeah.
So
that just reminds me of a Chris Monk piece of.
Yep, exactly. Yeah, he was saying something about focal length and
where it was focusing on the sea 10 miles away or something. Yeah, what an idiot! What an absolute moron! Jesus Christ!
So, anyways, I know this height, and so and of course, this is obviously a terrible way of estimating.
Oh well,
things.
By the way, if you want to know where the base of that lighthouse, I know exactly because I got a cartographer, the Isle of Man mapping service, to tell me that it was 43.7 meters from mean sea level to the
really
base.
Close to what I got. I think I got. Oh, I converted it to feet, but I think that's about
43.7 meters in God knows. I'll quickly do that calculation.
This actually might be a bit higher. Actually, this is.
Well, don't forget it's mean sea level. You might not have mean sea.
Yeah, exactly.
You don't know what conditions you've got there. That is 143 feet. 43.7 meters.
Shore height 148. So I'm actually taking the distance to this point, not the bottom. Right. Is this the bottom? Or is this the bottom?
Yeah, he said the base, so I presume he actually, when the cartographer told me, he actually meant the base, the very base of the thing. So that bottom of that white bit.
Okay. So I think this might have been taken at high tide then, I guess, because I'm getting...
Yes, I think that is actually. Yes, in my pictures shows more than that, yes.
Wait, no, let's think about this. Okay, so the distance from here to mean sea level... No, this is low tide because it's my value's higher.
Oh.
148. I think.
Whereas I just said it was 143, didn't I?
Yes.
143, yes. So there's a difference of 6 feet.
Oh, that's actually kind of nice, though, because that probably explains why everything matches so perfectly. Because if this was done, if this picture was taken at low tide, I'm not correcting for tide in any of my calculations on this side, because I don't know what to correct for the tide is. And I put in the tide error bars, and the, you know, plus or minus 10 feet is the error bar. If I include a plus or minus some leeway for the actual tide height. So I think our measurements are consistent.
Yeah, it's 3 or 4 meters. I think the variation normally. It's a little bit less.
I forget how much variation I put in. I think I put in, yeah, plus or minus 15 feet. Wait, how many meters is it?
I think it's about 3 meters, 3 or 4.
Either way.
Sorry, 4 meters. No, the range is 4 meters. So it's 2. So it's about 2 meters either way.
Yeah. Okay. So this is. Okay. Well, I'll have to be a little more careful about this.
2.5 meters. Yeah, it might be a total of 5 meters, 2.5 meters either way.
Anyways, that's, you know, that I guess that's kind of important. So maybe I should not present this because I need to make sure that everything is correct, because I don't want to put you know, piss anybody off, I guess, for not being accurate enough. Yeah, but let's just go through some of the images. Okay, so this is what the flat Earth model predicts under standard conditions, and, you know, assuming these numbers are correct, they can't be off by that much, probably a few feet. But it's clear that the amount of shore is much, much more than the amount of lighthouse.
Yes, that's a very good point. We haven't touched upon this, have we? The point is we're missing far more in the image. In fact, I might present my little diagram.
No, I think I have it here.
Great. Okay, brilliant.
Yeah.
Brilliant.
Yeah, so this is how much shore there is roughly. And so it's about a 1/4 to 3/4 ratio, right? This is 3/4 of this total height above the horizon. So that clearly is not going to match what we see here. Like I plot the ratios. So 26% versus 73% of this total height is the ratios for the image, and these are the predicted values. And obviously they're almost exactly opposite of each other, because in reality the shore is almost twice as big as the lighthouse itself.
Yeah. It's actually, yes, I think actually the ratio it is, yes, that's right. It's just over, very close to being twice. Yeah, 23 meters high, 43 point. Yes, it's just over. Yes, it's nearly twice the height of the lighthouse.
Yeah. Okay. Then I talk about the curve calculator. So this is kind of showing the difference between the refracted ray and the geometric straight line ray. And again, look at the scales here. This is a
110,000 meters
distance. Huge.
Oh, sorry, 50,000, right?
Yeah, it's 50,000 meters. And so if you look at how much it looks a lot, right, in terms of the y distance, but in terms of like the total arc length, if I looked at the average displacement, it would be, it'd be almost negligible.
Yeah. But we're obviously interested in those little meters, aren't we? So
yeah. So here I was looking at what happens as you change as a function of height. So we were talking about this earlier, and like I said, you have to be really careful about how much refraction there is, because you have to worry about the distance away from the target and so on and so forth. But so interestingly enough, what I find, so this is, I'm sorry, Rumpus, this is going to contradict you a little bit.
Oh, damn.
But it looks like the amount of refraction is the refraction acts in such a way that it effectively looks like it's lifting the object up, but keeping the proportions very, very similar to how they were in the beginning. Now, this is objects,
so you don't think there's any compression?
So,
so you're saying there's no compression, effectively?
I'm saying that, no, I don't think there's any compression.
Ah.
But the subtlety here is that these objects are contained within the Earth's atmosphere. And so you have to be very careful when applying this refraction to objects which are outside of the Earth's atmosphere. Because in that case, these rays basically go to infinity. And there is, yeah, it's not going to appear the same way as it was to something on the surface of the Earth.
Hold on, you're saying I'm not right, but surely the graph that I showed earlier about the elevation, the refraction effect, changing the elevation, and that bit about the star.
Oh, maybe I'm not going over. Maybe I'm not going over high enough.
That star thing surely demonstrates that what I'm saying must be true, doesn't it?
Yeah, but I think it's a subtlety because you're coming from infinity. You're coming from really, really far away outside of the Earth's atmosphere.
Right.
Like you actually need to integrate over all of the layers of the Earth's atmosphere. And I think the difference is this is happening on such a small length scale that really the amount of refraction, like the distortion due to refraction, is negligible. But as you go farther and farther out, I think that distortion probably should get larger and larger.
Okay, well perhaps we have to revisit
I can
that
actually let's actually just do this live.
Okay. Oh well, I'll write my own code, Phillip, at some stage in the near future, and then I'll compare so I can get it to.
Oh, I need to import the modules.
On me.
I have to do a little more detailed analysis.
Okay. Well, I think we've got the yes. I think let's just deal with. Let's try and sort of move to a roundup, perhaps. I think.
Oh, okay. Yes. Yeah. So I'm not going to present.
Let's leave with something fun to do when you come back after your 2-week sojourn, whatever.
Sure. Sounds good. Right. So what shall I end on? Well, basically, it seems like refraction we have a pretty decent understanding of, and it is, at least in my mind, it seems like enough to account for all of the observation of the Isle of Man. There might be some subtleties in nailing down the actual heights of particular objects, but this is actually a fairly not really important thing when it comes to the 100,000 data points which make up the entire profile of the Isle of Man. Yeah, you're going to argue about like a few feet when the entire mountain range of the Isle of Man doesn't match, and that is a problem for your model.
Do you need to count presenting? Do you need to count presenting?
No, I don't need to present.
Okay.
I'm just giving some remarks. Yeah, I think that's basically it. So yeah, the conclusion is if you model things realistically with real refraction, including atmospheric effects that you can document, things line up exactly how they should on a globe.
Yep. So the composite that Anthony took, or the video that we've got in composite, exactly matches your model with a. Okay, at the moment you think that you've got a refraction of 1.3, so we need to investigate that a little bit, because I say the measurements I've taken of the composite versus reality match very closely actually for standard refraction within a few meters, except for the Morgoth Lighthouse, which is off by about 7 or 8 meters. So I wouldn't. Oh God, I was
going
to
do hard calculations, right?
Yes, normal, just using refracted things, using a simple thing. And of course, what I should have gone into perhaps at some stage here was the drop and hidden, because of course that's what the flat earthers get confused about, the drop and the hidden. And we just need to say, I'm not going to go into it now, so we've spent long enough really. The drop is not what you should be using. Oh God, I could quickly screen share it just very quickly. That's just to make the point. I've got a whole thing on this, but let's just. But I've got a whole web page and a whole video in bloody ready to go on all sorts of things abuse to deliver to them. But where's the let's do it.
Wow, that's so much stuff.
It's just so much. Oh, what have I done with that damn? Did I put it in here? Or was that on my recent rant? Or was it on the other rant? Which rant was it? Oh God! Oh, this idiot! Oh, this is something aside. Yeah, I shouldn't really. This is this business about the horizontal.
Images, right?
Oh God! Yeah, I mean, just a quickie while we're here. I mean, although I was trying to keep this focused on your work. This idiot who thinks that that is horizontal, and this going on here, he thinks that that's normal. That's what's going on. Whereas if you take the staff out, you can see. Makes it clearer that is not horizontal, whereas in fact this line is. But yes, that's not really what relevant to this discussion. Oh, there we go. So here we go. It's a quick. People have seen this no doubt millions of times before. Right. So here we have an observer at 0 height, and this is our destination object. This is what's called the drop, and it has no. It is not function of height of the observer. So here we have an observer at A1, slightly an altitude of slightly higher. And they're looking down at this building here. So for this observer at A0 on the thing, the drop, it actually obscures completely this building. The obscured area is the thing in color here. When you're at this height here, looking at the horizon, you can see part of this building is H value. And of course, when you're dealing with images, as we're dealing with here, what you can and cannot see, what's going on with this drop is absolutely irrelevant. We're only interested when we're dealing with images. We're interested in what you can see. I mean, the only guideline, the only reference point is the horizon, which is this thing here. So what's going on, this geometrical construction about what's dropping, you can't see any of this. This is something you can't visualize. There's no sign in the sky saying this is where the drop goes from here to here. The only thing you've got as a reference point is the horizon. So that's the thing everything was with respect to. There's the dip angle. That's what you have to look down to see the horizon, because of course what you do is you look down until you see the horizon. At that point, that limits what the hidden part here of the object you're looking at. And of course, then if this line is bent, as I was showing earlier with my bendy lines of the lighthouse, and has been demonstrated by the bendy lines that Philip's been showing. So obviously, if the line starts here being bendy, I was going to include some refractive, but I'm getting around to it. A bendy line here, and obviously you'll be able to see, just like I showed earlier with the lighthouse, you would see lower down than you would just using a geometrical straight line. As we've established, light doesn't go in straight lines in the atmosphere. So the drop is just an absolutely insane, ridiculous thing. Then start talking about the bulge. Again, it doesn't matter the fact there's a bulge here. I'll do that in another video. But the basic point is drop is absolutely irrelevant. And the fact that Chris Monk suggested to and Nathan and Anthony Riley that they should be using that because he's an idiot. And they
unless
just,
you're literally all the way down.
Yeah, unless you're actually down the thing, of course, which means you can't see anything. It's no bearing on what you can see, has no value to that. And of course, because Monk doesn't understand hidden, doesn't understand maths, he just simply understood the word drop because he's used it from surveying days. In fact, here we are. I've got. Oh.
I mean, a simple way is like you're interested in the light which can reach your eye, and drop literally has nothing to do with what you can actually see.
Exactly, because the only reference point is the horizon, and I've got I've got the surveyor's drop somewhere here. Where's it gone? Where's it gone? Where's it gone?
Do they measure it from level?
No, the surveyor's drop. See, they don't take it from there. They actually take it from here.
Oh, I see. Okay, so it requires a little more trig.
Yes, exactly. Oh, where did I put that? This is the problem without me having a surveyor's drop. Surveyor's drop. Where have you gone?
Well, if you're on short enough distance.
Never mind. I've demonstrated this before on the previous hangout. God, it's learning the script for this is quite something. So anyway, so the drop is absolutely idiotic. Okay, so I think that's probably so basically you've corroborated the spherical Earth and you've invalidated the flat Earth model. Despite what Nathan claimed about what you were saying, and with Refraction, we've demonstrated the effects it has, quite considerable, non-negligible if you're worrying about tens of meters, but negligible in comparison to doing large mirage effects. So it's one person's negligible as another person's significant. Right, I think that probably does it. I think. Is it Philip? I think there's anything else we want to round out with?
Well, reality is more complicated than you think it is.
That's a very good thing to end on. I think we'll take it from there, Philip. So thanks very much. That was brilliant. And hopefully we'll do something again some other time.
All right, sounds good.